Okay. So let me introduce Professor S.C. Kothari in short. I welcome Professor Kothari. Fortunately, I met him in Pune. He had come to Pune and Bhaskaracharya Pratishthan. And then he said that he will not stay here up to this today's date in India, but he can give an online talk from US. So thank you, Professor Kothari. And so Professor Kothari is from Iowa State University. His topics of interest are algebra and algebraic geometry. Also, computer algorithms, solutions to industry problems, which he had done by starting a company. He had given earlier a talk in the University of Pune 2 years ago. And at that time, he explained how he could use his methods, and something which can be done in months could be done in a few days or hours. So that's why he had a solution to the industry problems, which was very popular. And he did PhD with Professor S.S. Abhyankar. In fact, he is the second Indian student of Professor Abhyankar, first being Professor Sathe, who is also here. So we are happy that we could get this time Professor Kothari. Last year, we had a talk by Professor Avinash Sathe in the same kind of symposium, Abhyankar symposium, and he also gave an online talk. Okay, so the title of today's lecture is Mathematics for Software-Enabled Technologies. So now I request Professor Kothari to share his screen and start his talk.
So are you able to see my screen?
Yes, we are able to see you, your screen, yes.
Yes.
See you.
Yeah.
So can you see the screen now?
Yes.
Okay. So thank you, Professor Katre. So on August 15, 1972, I landed in America to do mathematics with Professor Sriram Abhyankar. The person who came to pick me up from the airport is in audience, Avinash Sathe. And I have many fond memories of Avinash Sathe, his wife Shashi Sathe, and Yvonne Abhyankar in Lafayette. Now, 50 years later, it is a great honor for me to give Abhyankar birthday symposium lecture. I'm grateful to the symposium committee for arranging my lecture. So the need to understand the complexity of software has brought me back to mathematics. So let me share a timeline with you. So doing mathematics with Abhyankar meant something like this. We used to attend his seminars on Tuesday afternoons, often go to his house for nightly discussions. Every now and then, Abhyankar would throw a conjecture at you. The little ones were worth PhDs and the big ones were worth lifetime achievement awards. My PhD was about proving one of Abhyankar's little conjecture. During my 10 years in mathematics, I spent roughly 5 years on one hard conjecture with not much to show. 4 days ago, my mathematician friend Avinash Sathe told me that the hard conjecture is finally proved. Abhyankar called it the Jacobian Conjecture. Now, From 1996 to 2002, it feels now that I did an apprenticeship in software engineering. Students taught me a lot. They taught me nuances of software. During my apprenticeship, I realized the need for mathematical analysis of large software. It was apparent that a very sophisticated software apparatus is required to perform experiments to evolve new mathematical analysis techniques. So NSoft was founded in 2002 to build the analysis apparatus. The first 10 years at NSoft were a big struggle. In 2002, we had two major breaks. One was a large funding from DARPA. Now let's come to leader connection. So leader envisioned today's software-enabled technologies 60 years ago. Personal computer and the internet came out of the research programs he funded. His biography, The Dream Machine, is inspiring. Licklider was not a computer scientist. He was educated in psychology. He was an original thinker. His dream was human-computer symbiosis connected by a global network. So now, 50 years later, Licklider's dream is the reality. However, the new reality has brought with it unforeseen possibilities for life-threatening software failures and cybersecurity threats. There is a long list of catastrophic software failures. Here is a small list which shows the broad spectrum of failures from the plane crash to the biggest non-nuclear explosion caused by software failures. So software has intended behaviors. When the developers write software, they intend some behaviors. For example, a banking program, the intended behavior is that when the user is allowed to log in by giving the account ID and the password, but invariably softwares have unintended behaviors. And unintended behavior could be for the banking software. A malicious user may give a small program as the input for the account ID, and the account ID field may not be big enough to hold that program, and something weird happens, and the malicious attacker can hijack the computer. Given the pervasive use of software in all safety critical applications, there is an urgent need to analyze all possible software behaviors and identify and fix unintended behaviors. The problem is the soft infinity of all possible behaviors. By soft infinity, I mean it's finite, but it's so large that it cannot be enumerated by a computer, no matter how fast. So ultimately, we need another software to check all the behaviors, and that other software cannot simply enumerate all the behaviors and check them. So let me give a small example to illustrate the notion of execution behaviors. So the execution behavior is a subsequence of program statements, and for convenience, I have labeled the program statements here. So we have statements 2, 3, 4, 5, etc. And the execution causes each condition in the program to be either true or false and produces one behavior. So the execution behaviors can be represented through a truth table. So for this program, there are 3 conditions. Each condition can be true or false. And if we set all the conditions, we get one execution behavior, 3 conditions, so 8 execution behaviors. But depending on how the conditions are nested, some behaviors may be the same. So in this case, you can see that these 2 behaviors are same, another 2 behaviors are same. So the total number of behaviors is not 8, but 6. So the conditional statements and the loops create the soft infinity of behaviors. So for example, in a loop, the loop may have some iteration, I iterations, and for each iteration, let's say that there are n distinct possible behaviors. So inside the body of the loop, there can be branch conditions, and each branch condition creates 2 possibilities. So if we have 5 branch conditions, the number of possible behaviors in a loop will be 32. And so if we have I iterations and n possibilities for each iteration, we get n to the power I behaviors in a loop. So if we have 100 iterations and the conditions, 5 conditions within the loop, will get 2 to the power 500 behaviors, which is very large number, much larger than the number of atoms in the universe. So now let's formulate the heart of the difficulty is the soft infinity of behaviors. And let's now get to the mathematical formulation that captures the fundamental challenge of software-enabled technology. The first thing to note is that the software is a graph. So although, you know, if we look at the code listing, it looks like a string of statements. The way software behaves, it behaves like a graph. And we are going to talk about one such graph. It's called the control flow graph. And mathematically speaking, we can get the execution behaviors through the control flow graph. Control determines what statement could execute next. So again, let's go back to this small example. So we have these statements here, which I've shown as squares or diamond shapes. The diamond shapes are for the conditional statements. So we have 3 conditional statements at line 5, 8, and 9. So if it is not a conditional statement, there is a unique next statement to execute. But if it is a conditional statement, there are 2 possibilities. And so it's a binary relation. We can think of this as a binary relation, and it's called the successor relation. And we can view it as a graph. And here we'll construct the graph for this successor relation. And this graph is called the control flow graph. So what would execute next is defined by a binary relation called the successor relation, and its graph is called the control flow graph. So here are some examples of software graphs. So Xenu is an embedded operating system with roughly 10,000 lines of code. Linux, we all know. Apache POI is a Java program. So for Linux, the graph has about 26 million nodes, and it has about 77 million edges. The software graphs have sparse edges. So typically the number of edges is a small multiple of the number of nodes. The software graphs have many kinds of nodes for different types of program artifacts and many kinds of edges for relations between program artifacts. In the control flow graph, the nodes are for the program statements and the edges are for the successor relation. Now, various programming languages have in common, the program artifacts and the relations between program artifacts. Some of them are so fundamental that they are common to all programming languages. For example, the successor relation and the control flow graph is common to all programming languages. Okay. So now creating a software graph requires the knowledge of all possible program artifacts and the relations between those program artifacts for the given programming language. And so if what we need now is a schema to create graphs for software. And this is something we did funded by a DARPA project. We developed a schema called Extensible Common Software Graph Schema. The purpose is, we can create the software graphs which can capture the complete semantics of the program. And so this schema, for now, it works for a few high-level programming languages like Java and C. One particular language that is of interest to us is the Simulink. So the control systems we have complex control systems, and if those control systems fail, for example, imagine the control system for a power grid or the control system for a plane. So those programs are of particular interest to us. So that's a language that we support in XCSG. So here I have an example of how it looks for C and Java. So in C and Java, if we look at the node types are for program artifacts. Between C and Java, 206 common node types. So although, computer scientists may think that the two languages are very different, one is object-oriented, the other is not. But essentially, the two languages have a lot in common. And then the Java has 18 Java-specific node types, and C has 25 C-specific node types. Now, the edges are for relations between program artifacts. So, for example, the successor relation, and the story is the same here. A lot in common between Java and C. 53 common H types, and Java has 8 Java specific, and C has 14 C specific. So along with the schema, we developed front-end parsers for several programming languages so that we could take the programs in those languages and convert them into software graphs. Now, the software graphs have to be stored somewhere, and then we need to analyze them, transform them. So we developed a graph database for storing these programs. So one key challenge is that, these graphs are huge and we need real-time response. So, when we make a query, you want an instance response. For example, we want to know how many loops are there in the Linux kernel. So we want an instant answer, how many loops are there. So the other engineering challenge is to create the graph database and the query language. So this is something what we have been doing for last 20 years. And this graph database and the query language scale to handle millions of lines of code. So now next, go to the next step, the second step of the mathematical formulation. The first step is to view the graph as the software as a graph. The next thing is the execution behaviors can be viewed as paths in the CFG. Again, let's look at the execution behaviors for this program. We have already seen the truth table. Now we look at it as paths in the graph. So this graph has 6 paths from the root 2 to the end node 17. And every path corresponds to one execution behavior. And you can see that from the truth table, we have 6 paths, and there is a one-to-one correspondence between the paths in the graph and the execution behaviors. Now, the third step of the mathematical formulation. So remember, the goal is to find the unintended behaviors. So unintended execution behaviors can be characterized by a property of paths in the CFG. And we need to show that the property P holds on every path. And that's where the difficulty lies, because the soft infinity of paths. I'm going to show an example of a property which is very useful in practice. Many of the safety and security vulnerabilities which are reported in there are databases which are maintained, and every year they talk about how many violations were there, where they occurred. And there are thousands of vulnerabilities reported, but almost 80 to 90% of them can be captured by a very simple property. And the property is to show that on every path. So we have to formulate the problem in mathematics. Let's think that the nodes are colored. So a sparse set, a small set of nodes is colored. Some are red node, some are green node, and all the majority of the nodes are colorless. And what we want to show is that the red node is followed by a green node on every path of the graph. And the unintended behavior then can be characterized as violations of the property. Okay, so you may have heard of the terms such as buffer overflow, memory leak, race condition. All these unintended behaviors can be captured by this simple property. Again, let's look at a small example. This is stripped Linux code. So I have deleted many parts of the code to make the explanation simple. So in this code, you see lock and unlock. In a multi-threaded system, there are shared data structures, and multiple threads can access that data structure. And when a thread is accessing the data structure, it needs to lock it, because if somebody else accesses it at the same time, there can be corruption of that data structure. It is something like, you go to two machines, two banking machines at two sites, and simultaneously log into your account and try to withdraw money from your account. Those two transactions should not get mixed up. And so in multi-threaded programs, a thread must lock a shared structure, and it must unlock. If it doesn't unlock, then nobody else, no other thread can access it, and there will be a deadlock. The system will hang or crash. So often when you see a computer hangs, this is what happens. There is a lock, but unlock is missing on some path, okay? And then, later on, they will issue a patch, which is the unlock is inserted in the right place. Now, think of lock as red node and unlock as green node, okay? And now we want to verify that on every path, a red node is followed by a green node. So here is the control flow graph for the given code. And you can see that there is a loop in this code, this while loop. You see that here you start from while, you can go to lock, unlock, then there is a condition, you can come here and go back to the loop. So in this case, the loop has two paths. But on both paths, the behavior is going to be the same, because the unlock happens before the condition where it becomes two paths. And so on every path of the loop, lock is followed by unlock. But this loop has so-called exceptional behavior. And when the exceptional behavior happens, the loop is interrupted in the middle and you get out of the loop. So we see that if the condition 5 is true, we get out, there is a break, and there is no unlock. So what can happen is we enter the loop, we have a lock. Hello, I think there is some noise here. Hello, can somebody mute? Okay. So on this path, there is a lock, and if the exceptional condition happens, there is no unlock. And this is usually what happens, that there are corner cases where the developers don't think of some possibilities, and unintended behavior can occur. So I'm now showing the unintended behavior here. The star means whatever is in the parenthesis, that behavior can repeat 0 or more times. And when I write 3t, 3 is the conditional statement, and that is true. Okay, so we enter the loop when the conditional statement 3 is true. So let's summarize what we have discussed so far before we go on. So we have discussed the mathematical formulation for identifying unintended behaviors. There are three things. Software can be viewed as a graph. And the second is the CFG paths yield execution behaviors. And the third thing is we can characterize the unintended behaviors by defining properties of paths. The next thing is what do the existing approaches are, what are the existing approaches and where do they stand? So I've categorized the existing approaches in two buckets. One is software testing. This is the predominant approach. In fact, almost all software companies or the companies who have software-enabled systems, for example, the flight control system, they all depend on testing. And so companies spend a huge amount of money on testing. In testing, you are testing one behavior at a time. You give some input, run the program, and see if something bad happens, some unintended behavior happens. The verification is incomplete because there is no way to test all possible behaviors, the soft infinity of behaviors. And it's also very laborious to find even a single unintended behavior. Okay. So this is nowadays is called penetration testing, and companies pay tremendous amount of money for penetration testing, where the hackers can find unintended behaviors in software. So for this small program, there is a possibility of division by 0 because on line 17, we have z is equal to x divided by d, okay? And this has two inputs, a1 and a2 are the integers, and there are three Boolean inputs, c1, c2, c3, which are the conditions. So the total number of possibilities is large. The integers have the possibility 1 to 2 to the power 32, assuming 32-bit integer. So if we want to do testing and say that with 0.9, 90% probability that there is a division by 0 or not, it would require trillion tests. Okay, so you can see that even finding one unintended behavior can be pretty hard. The second thing which is in vogue in computer science is so-called formal methods. There's something called software model checking. These formal methods, they involve automated theorem proving. So my friend describes software model checking as follows. He says, you want to prove that this animal is a cow. So instead of looking at the animal and looking at some high-level features, what you do is get the DNA of the animal, do a DNA analysis, and prove that it is cow's DNA. So it's a very involved method. And there was a Turing Award given in 2007 for software model checking. So model checkers time out because of the soft infinity of behaviors. That's the issue. It's also very laborious to take a given software and convert it into a model which the model checker can check. And the conversion process itself can have bugs, and the model checker may be correct, but may give wrong results because the conversion is not accurate. The other issue with model checkers is blind trust on model checking. The machine says no invalid, no unintended behavior. It doesn't produce a proof when it is, and when it finds an unintended behavior, it does produce a counter example. Now, I think, mathematicians know that there is really no absolute proof. Like we were talking about Jacobian conjecture, there have been many proofs, and ultimately the way mathematicians decide whether something is true or not, it boils down to a community. So there is a social process in mathematics which determines whether something is true or false. Whereas in formal methods, the idea is trust the machine. And in fact, Perlis, who got the first Turing Award, writes about this, that how computer scientists have a weird notion of proving something and trusting the machine for the proof. And he argues that even if we are producing proofs by machines, the proofs must be human understandable. And it's been more than 50 years from the first Turing Award. The situation in computer science hasn't changed. So model checking of Linux, that's like a crown jewel, and lots of money has been spent on it. If we print Linux, it will be about 200 feet stack of paper. So it's mind-boggling size. The number of branch conditions in Linux is about 35,000. Here I'm talking about one particular version of Linux for which I'm giving the data. About 25,000 loops. Linux changes every day. Roughly 13,000 lines of code are added every day, 3,000 modified, and 5,000 deleted. So the best result available for using model checkers is by a Russian group. And this group has been funded for many years by the government. And it uses a BLAST model checker from Berkeley. So for this version of the Linux kernel, there are 50,000 spin locks and 28,000 mutex locks. I've taken a version of the Linux where they revise the locking design in the Linux kernel. There used to be many different kinds of locks in the Linux kernel. In this version, for the first time, they changed it so that there are only two kinds of locks, spin lock and the mutex lock. And so there was a major change in design and wanted to see if any issues because of the change in design. And the model checker has checked the previous design and found that there is no mistake, no unintended behavior. Now, the model checker, when it checks the new version, again, it doesn't find any unintended behavior. It can do about 2/3 of the lock instances. On 1/3 lock instances, it times out. So that's the category C3, and the category C2 is the unintended behavior. and C1 is no problem, all behaviors are intended. So wherever it could check, the conclusion was no unintended behavior. Now let's talk about a new approach where we are going to create an algebra for representing execution behaviors. So the first step is to define an algebra to represent and manipulate behaviors. So this famous quote by Kronecker, God made integers, all else is the work of man. You will see that we will define algebra, which is not on integers, not even on real or complex numbers. So in fact, the physicists define algebras to study physics. And here again, the algebra, like the physicist, is not about numbers. So the algebra is defined on the edges of the control flow graph. The multiplication is concatenation of edges. So, we have the edges E1, E2, E3. So if we concatenate E1, E2, E3, E4, E6, E8, E13, E14, we get a path from 2 to the dummy end node E. So we get paths by concatenating edges. And the addition is union of paths. So for example, if we have the expression E3 times in parenthesis, E4 6 plus E5, if you look at the figure, it gives us all the paths from node 4 to node 8. So we define an algebra. How do we use this algebra to get paths? So that turns out to be pretty simple. We can get paths by defining a linear system of equations in this algebra. So again, let's illustrate it. So we have the control flow graph. We have defined the algebra on edges of the control flow graph. Now let's obtain the paths from root to a node, okay? And like we do in any problem, when we are setting up the linear system of equations, the answers that we want to get, we use a unknown, a variable, and then we get the answer by solving the system of equations. So here we are going to introduce an unknown for every node. So for example, we will have an unknown for the node 8. Here for convenience, I will simply use the node number for unknown also. So the unknown for 8 will be x8, unknown for 9 will be x9, and so on. And now we are going to set up a system of equations using these unknowns. So we introduce unknown for each node. Next, we are going to set up an equation. The equation is set up using the predecessors of a node. So for example, if I want to set x8 equal to something, I'm going to use the two predecessors, 6 and 5. So the equation is going to look like this. X8 is equal to x5 times something and x6 times something. I'm sometimes using the multiplication, sometimes the multiplication symbol, sometimes I'm leaving it out when it is clear from the context. But here I want to specifically say I'm going to multiply x5 by something, okay? And you can see it's very, if we have all the paths to x5, multiply by E5, concatenate those paths with E5, and we will get the paths to E8. Similarly, concatenate the paths to E6 by adding to the node 6 by adding E6, and we get paths to 8. So the equation becomes x set is equal to x5 E5 plus x6 E6 times x6 E6. So this is the equation for node 8. Okay. So now we know how to set the linear equation. Now let's solve the linear system of equations. So first I'll set up all the equations for each node. So these are the equations for the nodes. Now we can do back substitution. It turns out that the way the software graphs are, the solving the system of equation doesn't require a cubic algorithm. We can do it in linear time using the back substitution, and we get this result. So for x17, we got the result, and you can see that if we multiply it out, we will get 6 terms because we have a parenthesis with addition and another parenthesis with 2 additions. So when we multiply, we get 6 terms, and each of those terms will give a path in this graph. So I'm listing here the 6 paths we will get, okay? Now there is an interesting twist. Let me see what's the time, okay. I think it's already 8:02, but we started 10 minutes late. So I think I should be able to finish
Yes,
in
yes,
10
only
minutes.
10-15 minutes are there, yes.
Okay. So interesting twist. Typically when we solve system of equations, we may have to divide, right? In the previous example, there was no division, okay? But are we going to have the need for division? It turns out, yes. So let's say that we have this equation, x1 is equal to E0 plus x1 times something. And then, we get x1 is equal to this. Now, this is a weird looking, does this represent any path? We have 1 divided by 1 minus E1, E2, E3, right? And what path does it represent? And actually, I was stuck at this point for several months. So as I was developing this algebra and trying to see how it could be used for software. First, I thought maybe there is no need for division, but soon, very quickly, I saw that there is need for division. And what is this division? What does it represent? Like, we have ring of matrices and some elements are invertible, okay? And what does the inverse represent, okay? And I was actually pretty depressed. I thought I'm on a good track here to create a mathematical method. And then it looked like it's not working. And I very distinctly remember the Sunday morning when I woke up, I knew the answer. And in fact, the time when I was lying in the bed, there's something that I've learned from Abhyankar, and Abhyankar came to my mind. Abhyankar used to say, don't be afraid of infinite series. Use them and things somehow work out. So here an infinite series comes to help. So we know that 1 over 1 minus p is this geometric series. And if we think of P as a path, then what this tells us is one, P is repeated 0 times, P is repeated 1 times, P is repeated twice. So this is nothing but a loop. 1 over 1 minus P is a loop in a graph. So we can represent it as P star, the notation which I introduced earlier. So really,
This to this is not working.
are you saying something to me? Okay. So here is an illustration. Here is a simple graph with a loop. The path in the loop is E1, E2, E3, E4. And if we set up the equations, we get the situation where we need division. And now we know how to interpret division. And we get the correct answer. So actually, division provides a way to handle loops. And it works for all kinds of loops. Loops can have multiple paths, loops can be nested, and so on. It can be shown that this will always work. Here, I'm giving an example of a loop where there are two paths. The loop starts at 1. We can have 1, 2, 3, 5, come back to 1. Or we can have 1, 2, 4, 5, come back to 1. And even here, if we set up the equations, solve the equations, we'll get the right answer. The other thing that happens with algebra is we have the concept of homomorphism, and we can define homomorphisms. And the way we can use homomorphisms in software is to find relevant behaviors. Okay. So for example, here the property is about lock and unlock, and we want to find behaviors. For example, this if condition, it really creates two behaviors, but it doesn't have any effect on checking whether lock is followed by unlock or not. And so what we can do is we can factor out the irrelevant behaviors by applying a homomorphism. So if we take the behavior for the, this is the all behaviors for the given program. Here I am representing the behavior using nodes. When I set up the equations, I used ages, but the expression that we get for ages can be easily converted to an expression for nodes. And we get these relevant behaviors by applying a homomorphism. And, this has two behaviors because, we are multiplying. In parentheses, we have one addition. We get two behaviors, and one of them is the unintended behaviors. So especially when we are dealing with large software with Linux, this algebraic method becomes very powerful. It can deal with a very large code and get us to the heart of the code that we need for finding unintended behaviors. So this is what we have discussed, the mathematical formulation, the existing approaches, and the new algebraic approach. How promising is this approach? So let's go back to the lock-unlock verification of Linux. We looked at the result for model checker. Now we check the same thing using the algebraic method. And first of all, more than 99% cases could be handled completely automatically. And the algebraic method doesn't time out, but in some cases, it identifies the difficulty which, where the automation is not good enough, and then it alerts the human that you have to look at this case, and it gives what it has found about the case so that it becomes easier for human to reason about those cases. So there are about 400 cases which the automated method referred to the human. But the more interesting thing is it found unintended behaviors, which the model checker failed to find. So these were the problems which got created when the design was changed. And interestingly, one of the unintended behavior is a behavior which the model checker certified as all right, that it is an intended behavior. So the model checker clearly is not foolproof. It is making mistakes. So what else? We get a good result for the Linux kernel and for other verification problems. But, like mathematics is kind of, Thurston says it gives us a deeper understanding. And with the deeper understanding, we can think about things which have not been thought about before. So for example, some mathematical explorations, let's look at one example. So we have a graph and we have the expression for all paths in the graph. I'm going to show you 3 examples. The second one is the DBZ control flow graph and the expression for all paths. And this third one is a messy graph. It's a program with lots of go-tos. And again, the algebraic expression, okay? So if you look at these algebraic expressions, they reveal something. So for example, in the first one, E2 occurs twice. There is a repetition of an age. In this second one, the DBZ, no repetition. So the algebraic expression, every age occurs exactly once. And the third messy case, E6 appears 6 times. So the algebraic expression gives us a new way to measure complexity of the graph structure. And in computer science, people talk about structured and unstructured graphs. There is no clear definition. There are hand-waving definitions of structured and unstructured. And Donald Knuth, in fact, wrote a paper 40 years ago and talked about how even the concept of structured and unstructured programs is not well understood. So in fact, I showed this method to Donald Knuth to answer the question he posed 40 years ago. The other thing is a lot of algorithms about graphs can be done differently. And if the graphs are sparse graphs, which is the case often in practice. So for example, the Facebook graph is a sparse graph. You can have many friends, but the number of friends is not of the order of total number of people in the with Facebook accounts. So there are efficient methods to solve directed graph problems using this algebraic method. So you may want to do as an exercise an algorithm to find the shortest path or to create the dominator tree. So, doing this research required tremendous amount of engineering effort. For example, defining the XCSG, creating the apparatus to transform software into graph. And this engineering was done mostly at NSoft. And my students at Iowa State and colleagues at NSoft, without them, this research could not be done. And not only engineering, they have taught me many nuances of software. I've never had any course in computer science. So, without their help, I could not have done this journey. The DARPA, without the millions of dollars of funding we got from DARPA, it wouldn't have been possible to do the engineering we did. And I'm in particular debt. There is one program manager who, not only trusted our research, he asked many penetrating questions that have helped us evolve our technology. Last but not least, my mentors in software engineering, Ramamurthy and Donald Knuth. It was pretty hard, coming into software engineering with no formal education in software engineering. In fact, when I sent this algebraic method to Donald Knuth, I got a postcard back from him. I'll show it at the end. I spent 25 years working on this problem, tried all kinds of things which looked very complicated. And there are many others who have tried things which are even more complicated. It turns out the answers can be pretty simple using mathematics. And like Steve Jobs says, simple can be harder than complex. You have to work hard to get your thinking clean to make it simple. So it took me 25 years to get my thinking clean, but there is a reward for it. You can move mountains. So this is the postcard I got from Donald Knuth when I was, the paper he wrote 40 years ago and talked about there being not a clear way to define structured and unstructured programs. And using algebra now, we can define the concept of structured graph and non-structured graph. Okay, so I'll stop here.
Yeah, thank you very much, Professor Kothari. So let us give him a big hand. And if there are any questions, especially because some computer scientists are also around, I think some speaker, some of the audience. So any questions, most welcome. Prashant, you want to say anything? Yeah, please come. So he's in the audience here at the Bhaskara Pratishthan. He had something to say.
Can I get the name again? Who is the person?
Yeah, he is coming here. His name is Prashant.
Okay.
He was our regional coordinator also for Maharashtra and Goa Olympiad up to last year for 3 years, and he is working in a computer company. Yes.
Okay. Hello, Prashant.
Hello, sir. Yeah, it was a very nice lecture to listen. Maybe just a quick question is that how I think your approach really nicely captures the various paths that can be taken. But what about the expression that is actually executed at each node? So how do we capture
So
the
I
complexity?
think what you are talking about is data flow, right? And there are two major aspects of a program, the control flow and the data flow. And yes, that needs to be captured. But typically, the way computer scientists have tried to do it, the existing approaches, it becomes difficult because they don't deal with they don't do a path-sensitive analysis. They group the paths together. But once now one has a way to handle the soft infinity of control flow paths, one can do a data flow analysis which is path-sensitive. It can be then very accurate. So we can talk about it sometime later, but I think, right, your question is valid, but I purposely didn't cover it to remain focused on one problem.
Okay, yeah, makes sense. Thank you, sir.
Any other question or query? If anybody in the audience wants to say something, comment or question.
I have a question.
Yes. Hi, Gurjar.
Hi. So is there any other kind of mathematics which is useful in computer science or only graph theory mainly? Of course, you are
Uh,
trying to use algebra now.
Yeah, see, the software is a graph, right? So obviously graph theory is useful, right? But now one can see that one can define algebra on graphs. So computer science, in particular software engineering, is a very nascent field. And the kind of mathematics that would be valuable for is still being discovered. And unfortunately, the computer scientists are they create buzzwords like artificial intelligence and many other things, which from a mathematical viewpoint are pretty simple. And so as a result, what has happened is the computer science can really benefit from progress of mathematics, which hasn't happened because the mathematical mindset is missing.
I see. Okay.
Yeah, okay. So any other comments, questions, if are there? Otherwise, we will stop now. So I thank again Professor Kothari. Thank you very much. A totally different talk. I mean, and how mathematics is used in the software programs also, and certain things which one has to keep in mind, that you have very nicely explained. And although this was online and offline, so this is new thing, hybrid mode we have tried after the pandemic, and it will be more and more successful. Many people could join, but those who could not join for some other constraints like teaching and other, so they can see these lectures on YouTube in the Bhaskaracharya Pratishthan YouTube channel. So that will be available. So you can tell your friends that these things will be available. Many other lectures also Bhaskaracharya Pratishthan is organizing, like Triangle Group series that is being organized, and the lectures in that they are put up on the Bhaskaracharya Pratishthan YouTube channel. So one can see those lectures there also. That is what I wanted to tell all of you. And I thank all who have attended. Some teachers, college teachers have attended from Pune and from other places. So thank you all. And Professor Sridhar Abhyankar was also here. He is also there actually. And very patiently he attended the whole session, although he is, I mean, in spite of his very old age, he took keen interest and he attended. So I thank him also. And many others,
Yeah, thank you,
Okay.
Professor
Yes,
Katre.
yes, thank you. Yes.
Yeah, and it was by chance that I met you at the Pratishthan, and it's really an honor for me to give a lecture to honor Abhyankar. Yeah, thank
Yeah.
you.
Yes.